Okay, so my name is Monika Nawrot. I came with Marek Biskup. We are both from Google. We are based in Google Warsaw. And we are going to talk about what's under the hood of serverless platforms. So we both spent 4 years building Cloud Functions, one of the top major serverless product in GCP, and that's why we are here. So this is the agenda of our talk. So first, I'm going to talk about serverless, so what serverless is, and also what products do we have in Google Cloud Platform that are written in this paradigm. Then we are going to talk about what's under the hood, so about specific implementation details that affect the system, how, in a sense that you will know how to write serverless systems, and also you will be able to reason why it's that. And finally, we'll walk you through the real-life example. So we'll show you a serverless application, and we do a bunch of steps to optimize it, and we'll show you how it works on Google Cloud Platform. So first, what is serverless? So I'm sure that you all were on the keynote when it was very well explained what serverless is. So just let me recap what was said there. So in serverless, there are no servers. So you as a developer don't even think about the concept of a server. So you don't have to care about, I don't know, virtual machines, about operating system, about maybe applying security patches, updating the security system. You don't have to think about configuration or anything which is related to server management. The second thing that is specific to serverless is that it scales automatically. When I'm talking about that, I'm talking about two problems that we are solving. So the first is 0-to-1 scaling. So let's say that your application doesn't receive any traffic, then we can shut down your instance completely and it's not running. However, when there is a new request, there's a new traffic coming, then we can bring up your service. And the second scaling is from one to many. So let's say there is huge interest in your service and there's a traffic spike. So then we can spin up as many machines as is needed to handle this traffic. And the third thing about serverless is that you pay only for what you use. So for instance, you are paying only for the time when a request is being processed, not the time when your machine is idle. So it can be compared with services that are running on virtual machines. When you buy a virtual machine, it doesn't matter how much traffic it handles, you are just paying for the time that machine lives. Yes, but this is a very abstract definition. So let's see how it looks on Google Cloud Platform. So let's think about an application. So usually you need to have these 5 layers. So on the very bottom, you need some hardware. So you need to have some bare metal machines on which your software is running. On this hardware, you have some sort of operating system of your choice. On the top of that, you have application runtime. So it can be some container service that is running containers, or maybe it's a web service, or maybe some database. So these kind of services that support your application. And yes, finally you have applications, so all the code that is written that implement business logic, that's something that you write as a developer. And also when you think about application consists of several functions that talk to each other. So function is probably the smallest abstraction that you have in your application. So now what kind of architectures you may have? So on your left, you can see a situation when you have to manage everything. So this is probably on-premise service, when you have your own data center, your own machines, and you have to manage them. You need to install operating system, application runtime, then you can deploy your application that consists of functions. So everything is your responsibility. When you move to cloud, you can choose between these 4 other architectures. So first you have something which is called infrastructure as a service. So here you don't have to worry about the hardware. This is something that we as a cloud provider gives you. You're just choosing a VM, you deploy it with your chosen operating system, and then you need to enter the machine, so SSH to the machine, download some web server, for instance, install it, deploy some application, and set up some wiring so it's available externally, and then you can run your service. And then when we move to the more highly managed services, we have container as a service. So you run a container. So here we have two solutions. We have Cloud Run and we have Kubernetes Engine. So here you don't worry about VMs, you don't worry about operating system. You're using some kind of container running service. There's, of course, you need to configure it. You need to, for instance, you need to choose the number of virtual machine, virtual clusters when these containers will be deployed. You need to configure some things related to scaling, for instance, etc., etc. But on the top of that, you can just run a container with your application, and that consists of functions. Then when we move even further to the right, there's App Engine. So with App Engine, you deploy application. So the only thing you need to write is the application code. And you can take this code and put it on a platform, and it's up and running. And we call it application as a service or platform as a service. And finally, on the very left, we have function as a service. So you as a developer write a function in your favorite language. So a very small code snippet that does the one thing. You deploy it, and everything is up and running according to this paradigms that I mentioned before. So these are your options. I will be talking, or we'll be talking just about three of them. Like the most abstract one, the most managed ones. So Cloud Run, App Engine, and Cloud Functions. So I will talk about these three solutions in the historical order, just to give you some understanding how this platform evolved, because like every product learned something from the previous product. So the oldest one is App Engine. And the aim of App Engine was to make it very easy for developer to run, build, and scale their web applications. So we are like on this App Engine vertical. So what is App Engine? So App Engine was started a long time ago. So the first version was run in April 2008. It was serverless before we even named the services serverless. It was cloud before Google Cloud existed. And that was like a very different times than we have today. So just to give you a reference, the first Android version was developed in late 2008. So in 2008, we really weren't even talking about mobile. It was mostly about web. That's why App Engine focused on web developers and allow them to focus on code. So as a developer, you just needed to create your application, the business logic, and it could be deployed to cloud very easily. App Engine also started as a very opinionated framework for writing web applications. So for instance, if you wanted to log something, you needed to use a specific library shipped with App Engine that you needed to call so you could see your log. So you couldn't use your the most common library in each language, or maybe just write to standard input, standard output, or standard error. However, it was in 2008. Right now, we have something which is called App Engine second generation runtime, which doesn't have this limitation. So you can use practically the same code that you're running outside App Engine and deploy it in App Engine. Also, because it was started a long time ago, it's a very mature product, which means that there are a lot of features that App Engine provides. So you can, for instance, decide whether you want a stateful application or stateless, whether you want it to be multi-threaded or single-threaded, etc., etc. So why would you use App Engine today? So first, it's like optimized for web serving workflows. So if you want to develop a website, that's a perfect choice. With App Engine, you focus on code. So the only thing that you need to write is really code. It's also great for variable load because App Engine operates on quite powerful instances that can handle usually more than one request. So even one instance can handle traffic that is changed. And also you have many, many features. So we have things like versioning, like traffic splitting. You have HTTPS endpoint like out of the box whenever you deploy App Engine, and many more. And finally, App Engine is very popular today. So it handles 320 billion requests per day. And that's really a lot. So just to give you a sense of how much is it, based on publicly available data for Wikipedia, we counted that Wikipedia, which is extremely popular service and is also very read only when you browse different pages. So Wikipedia handles 270 million requests per day. So there's 1,000 different in the order of magnitude comparing with App Engine. So it's really one of the biggest services that we have in the world. So very short demo of App Engine. So let me go to console. So here I have a Hello World application. This is the configuration file. It's very basic. So there are many options that I could possibly configure, but here I can just inform that I have a runtime in Go, and there is just one handler for the URL. And this is the actual application. So you can see that it's Go, but I hope you can all read it. So it just registers a handle. So handle is here, so it just takes HTTP request and response and prints something. And that's really it. And so this is the simplest App Engine application that you can write. So I can use gcloud, which is a command line tool that can be used to deploy or manage all services or resources that we have in Google Cloud. And it also includes App Engine, so you can deploy from a command line to the cloud. So I have some parameters here. So this will be a URL on which my application will be serving. So it takes a little while just to deploy a new version of application. Just to let you know, I have it already deployed, but right now I'm deploying a new version. So all the traffic will go to this new version of the application. So I can also show you the console. So here is App Engine. As you can see on the left, there are many other services that are very well integrated with App Engine. So here I can go to versions. Let me check. Okay, the application has been deployed. So here I have all previous version of my application. This one that I deployed in a second is handle the whole traffic. So here I can click to just go to that version is the application URL in appspot.com. So it was very easy. The only thing that I needed to provide was the application itself. Then Google Cloud Functions. So App Engine was developed in 2008, and around 2016 we launched Google Cloud Functions. And the aim of Google Cloud Functions is to provide an event-driven serverless compute platform. So we are on this very end of the fully managed infrastructure. So why Cloud Functions? So Cloud Functions can be used to build and connect different cloud services. And also what's very specific for Cloud Functions, it's not only about HTTP, it's also about several other what we call event providers, like Cloud Storage, Cloud PubSub, Firebase services. So thanks to Cloud Functions, you can very easily connect different services using different event mechanisms. To give you an example, you may think about a pipeline when you have, let's say, some batch jobs that daily produce some data that you would like to analyze with BigQuery. So Cloud Function can be something that will be triggered at the moment the new data appeared, and then Cloud Function will run a BigQuery. So Cloud Functions is available for several runtimes, several languages, and it includes like Node.js in different version, Python, Go. And there will be more. And this is also something that you might be interested in. It is a Java conference. We have Java in alpha. Alpha means that the access is closed. It's not something that's available for everyone. However, with this QR code or this link that is on the bottom, you can subscribe for this access, and you can start writing functions in Java before the others. And also you will have access to the user group for Java testers. So you can possibly influence how this feature will look like. So I highly encourage you to use that link if you are interested in writing Cloud Functions in Java. So event providers, because that's crucial about Cloud Functions. So of course, you have HTTPS. So thanks to that, you can integrate Cloud Functions via webhooks. So many services allow integration of these kinds. For example, you can write custom actions in Google Assistant, or you can write custom commands in Slack, or you can react to some changes in GitHub. You can integrate with Google Home and several services like that. IoT is usually this way. You have also like native integration with Google Cloud Storage, Cloud PubSub. So PubSub is our messaging system. So you can connect it with practically any cloud service that publishes to Cloud PubSub, or you can publish your own messages. And finally, Firebase. Firebase is a platform that is targeted for mobile and web developers. And it makes it very easy to write a backend application. So for instance, there's a Firebase database that can be where each change in the database can trigger a function. So thanks to that, you can write some backend logic just in response to changes in the database. So you can think that you have a mobile app and there's a new person that registers in your app. You store some data about this new account in the database, and there's a cloud function hooked, and this cloud function will send an invitation email to this person. So you can write a simple function that actually does that in response to these changes. So why cloud functions? First, when you would like to run a code that responds to events, so not only HTTP, but also is very well integrated with other services that are written in this publish-subscribe model. Cloud functions are great for extending existing cloud services. And also they provide a very good developer experience, because the only thing you need to write is a simple function. And they're easy, it's a very easy model. So you can really understand how they are built. You can reason why they behave in a specific way. So Cloud Functions demo. So let me go again to my Cloud Console. And let's go to Cloud Functions. So I have several functions deployed, but I will create a new function. Function hello. Maybe that way. You can choose the memory that will be available for the function. You can choose a trigger. It will be HTTP with the URL like that. I can choose the runtime. The code is pre-populated, so as you can see, it's a very easy, like very simple hello world function that just will print hello world if there's nothing in the request, and that's it. And so I can click create, and right now my function is being created. it will take a while because there are several steps that are happening under the hood. So the first thing, we need to build a function, which means that we need to build a container. Then we need to deploy this container to our infrastructure. And finally, what we do health checking. So we're trying to load your function. And this is actually quite important step because when you write cloud functions, you often put some logic into what we call the global scope. So whenever you have some error in this piece, we will inform you why deployment. So my function has deployed, so I can go to this trigger section, and I can trigger my function. And again, I see hello world, and we can see this nice URL here, which is pointing to my function. So it's like fairly easy because we have just a few lines of code that are now available in a few seconds. So that was Cloud Functions. And finally, Cloud Run. So Cloud Run is the newest service in serverless paradigm that is available on GCP. So it aims to run stateless containers available via HTTP. And what's interesting, Cloud Run really comes into flavors. So you can choose this fully managed version when we manage your containers, but also you can deploy it on your own GK cluster. So we are just in the middle if it goes to this management axis. So Cloud Run, which was announced on Google Next in April this year, is a new serverless solution that aims to run containers in the serverless fashion. And containers is very important here because they offer flexibility and portability. So you can have the same container that is running in Cloud Run, that is running on your local machine, that is running in your own data center. So you don't have to apply any changes to that. And this is because Cloud Run is an implementation of Knative. So Knative is an open source initiative that is driven by several companies, including Google, that aims to standardize running containers and managing these containers in this serverless fashion. So why Cloud Run? Cloud Run mostly because of the containers that I just mentioned, about the fact that you can deploy them everywhere, and also because of lack of limitation on the language, on the library, on the binary. You can run everything on a container. And finally, it's also about open source. So open source is cool, so why not to do that? So let me show a quick demo. So again, let's go to Cloud Console and to Cloud Run. So I will create a new service. Here I need to provide address of the container. So I will use the publicly available image. So Cloud Run provides such images. One of them is hello with hello world. Here I can choose, service name. I can choose the location when it's deployed. All serverless solutions at Google are regional, so you can use a region, whether it's somewhere in Europe or maybe somewhere in the US. That's your choice. And I click deploy, so a new version is being deployed. It's ready, but let me show you the YAML file. So this is like the core of Knative and also of the specification of Cloud Run service. So here you can see a reference to the API version. It's just show that it's pretty new because it's alpha, and you can see like several parameters that reflect the current state of this service. So here I have URL. So I can click to that and go to that application, and you see it's up and running. It contains some metadata from my service. So that was a quick demo of Cloud Run. And now it's time for the next point in our agenda. So let me invite Marek, who will talk more about what's under the hood of these services.
Thank you, Monika. Hello, everyone. I'm very happy to be here. I'm so glad that so many people showed up, even though it's pretty late. So you already know what serverless is, how you can use it. You know the 3 platforms that we have at Google, and now I'm going to tell you how it works underneath, and show you how to optimize the code to be more efficient and actually to pay less. So what I'm gonna talk about is very much focused on Google Cloud Functions, but I believe in other platforms things are very similar. So I'm going to tell you where the code is executed, how it's executed, and how do you pay for that. Let's start with where the code is executed. At Google, we have a shared infrastructure for all our services. It's called Borg. On Borg, we run the search, we run YouTube, we run Google Maps, everything runs on Borg. And of course, we also run your code when you deploy a cloud function on Borg. But the problem with your code is that we cannot really trust it. You can write anything that you want, and we have to make sure that, first of all, you don't break our search, you don't break Google, and maybe more importantly for you, we have to make sure that other users cannot interfere with your code. So we do that using gvisor. This is an isolation technology. This is something very similar to what was mentioned on the keynote in the morning, the Firecracker VMs in AWS. We use gvisor. It's a sandboxing technology based on containers, but it very much solves the same problems. I don't think you should be so much it should be pretty transparent for you. It doesn't matter how we isolate things. What you need to know is that we do isolate your code from all the other code. The code is executed on instances. I just mentioned that gvisor is a container-based isolation technology, so we run containers. Everything is in containers. And those containers are actually long-lived. It means that when we execute, I will focus on cloud functions, maybe for simplicity, but with Cloud Run, App Engine is pretty much similar. So when you run a cloud function, when you invoke the function, and the function finishes, we don't shut down this container. We will reuse it in the future so that your code can be executed more efficiently. You don't have to reinitialize all the same global variables that you already have. So instances are long-lived, and then they are auto-scaled. When there's a lot of traffic, we will set up new instances so that they can handle multiple requests in parallel. But of course, every instance, we handle just one request in case of cloud functions. And every instance is dedicated to just one function type. If you deploy multiple functions, all functions get separate set of instances. What can you execute inside this container? Basically anything. So even though the runtime that you choose is either Node.js or Python or Golang or whatever, you can actually execute any shell binary. And this is a very nice example of a function that allows you to run bash, to run just binaries. And you can use it to check the user that you run with. It will turn out to be root. You can check what's on the file system and so on. So I actually encourage you to go to Google Cloud Functions after this talk and actually check what the execution environment is. How is the code executed? You know that it's executed on instances, and now the question is how we start those instances and when we shut them down. So we maintain some set of instances for every function. When there is no traffic, we sometimes actually get rid of all the instances. But of course, when there is traffic, some instances are actually handling the traffic, but some instances may remain idle. And when a new request comes, we actually try to find an idle instance to run it. And this is actually very good for everyone. So it's good for the cloud provider, because then we don't waste resources to starting up another container. And it's also good for you because you will have all the instances already initialized. For instance, if you have to download a large machine learning model to your instance, you can do it only once, and then this instance will be reused for classification in subsequent invocations. That's a use case. So when this instance is busy and another request comes and there is no available instance, we'll start a new one. And this is called a cold start. Cold start in the sense that it will take a little bit longer to warm up the instance, to start it up, because we have to do more things. I will talk about constants in a minute. And then the instance becomes busy, it handles the traffic, the request finishes, the instance is idle. And of course, we do keep those idle instances for some time, but we don't keep them forever. Because after some time, they become just unused and they waste resources. So we evict them. So let me come back to the cold starts. Cold start, as you already know, cold start happen when there is an invocation of your function, of your code, and there is no instance that is available to serve the traffic. What happens during the cold start? First of all, there is some scheduler that decides on which physical machine the container will actually be instantiated, where the instance will run. Then we start the container, and then we run the language runtime. So for Node.js, we start the Node binary. For Python, we start the Python binary. For Golang Java, for Java, we start the VM, JVM. And those three steps are actually entirely on the cloud provider. So even if you want to optimize that, you don't really have so much possibilities. This is good because you don't actually want to optimize for that. This is a serverless platform. You don't manage servers. But the last part is loading of your code and initialization of the global variables, for instance, in the code. So we load and initialize your code. And this is the place when you can optimize. What can you optimize? For instance, if you use many dependencies, they will all be loaded one by one when we load the code. So, for example, in Node.js, you have the require statements on the top, and we will execute all the require statements, and it takes time. So if you have any unused dependencies, just get rid of them. Cold start will be faster. Your code will be running faster, and you will actually pay less. This sounds like a very easy optimization to just remove the things that are not used, but sometimes it's not so clear what is used. Sometimes you load a very large library, which internally includes many small ones, and you don't really need the large one. You need just one of the small ones. So this is some optimization that you can use to speed up your code. You can actually do also lazy initialization. If you think that some part of the code will not be used in every invocation, you can actually initialize it lazily later to save time. A very good idea is to split a large piece of code into smaller pieces so that every one of them loads quicker. On the other side, there are cold starts, which happen when there is already an instance that has previously served a request. And during cold start, you already have everything initialized. And to speed up function invocation during cold starts, you can also do some tricks. For instance, you can reuse network connections. Establishing a network connection always takes time because there are those packets that fly over. And sometimes it makes sense to actually keep a persistent connection and reuse it in the future invocations. Not always. Very often, if the server that you connect to is very close, for instance, in the same cloud region, it's actually better to reconnect. But sometimes it's better to just preserve a persistent connection. And also some objects that you initialize don't depend on the request. For instance, if you train a machine learning model and then you use it for classification in a cloud function, the first thing that you do is to download the cloud ML model from, let's say, cloud storage. And this takes time. And of course, you don't want to download that from the cloud storage every time there is a new request. It's enough to download it only once. So talking about the cold starts, there is actually a small difference between different platforms that Monika described, between Cloud Run, App Engine, and Google Cloud Functions. In Cloud Functions, I told you that before, there is just single request handled in parallel on a single instance. So there's single concurrency. And on the other hand, in Cloud Run and App Engine, you can configure multiple concurrency, and that's the default. And of course, if there are multi-concurrency, there will be fewer instances. So you can expect that in Cloud Functions, you will actually have more cold starts because there will be more instances. Every instance is single concurrency. On Cloud Run App Engine, there will be less instances. So of course, when you have many cold starts, you want them to be very quick. And if there are few cold starts, then you want them quick, but you don't care so much. So depending on how long it takes to initialize your code, you can choose either Cloud Functions or App Engine or Cloud Run, up to you. And of course, it doesn't make sense to run a very complicated binary that initializes a long time on Cloud Functions. But of course, you can always run anything on App Engine and Cloud Run. I will talk about differences a little bit later as well. So things to remember here is that you should probably not pretend that your large monolith is actually a microservice. Is it fine to run such things on Java, on Google Cloud Functions? Probably not, because it will take very long to cold start. So maybe you should run this large monolith on Cloud Run and or App Engine. On Cloud Run, you just run a container, so it should work, right? The answer is, well, maybe it's not such a bad idea. You could do that. But of course, the nicest thing is actually to split those things into multiple discrete services, and then you can run it everywhere. So complicated code will take longer to initialize. It's better to split it. Microservices are quicker, faster, better. How do you pay for executions of your code? It depends. Every service has a little bit different billing model. Google App Engine is the oldest one, and actually it's a little bit visible in the pricing. So in App Engine, you will pay whenever the instance is running. So you will pay also if your code is not being executed at a certain time. Of course, we will take care of shutting down instances that are not used. You can actually configure that in whichever way you want. But usually the price will be a little bit higher than in Cloud Run or Functions. In Cloud Run and in Cloud Functions, you pay only when your code runs. When when the last request is finished, we will freeze the container that executes the code. This means that after request processing finishes, you will not be able to do any things like mine Bitcoins, and that's because you don't pay for that. Cloud Functions are slightly different because they are single concurrent, so every request comes to a separate instance. You may think that this may actually be much more expensive than Cloud Run because you will pay for multiple instances, but it's not always the case. In Cloud Functions, those instances can be very small. As you can see here, they are smaller. In Cloud Functions, you can configure small amount of memory and small amounts of CPU, and then it becomes actually cheaper. So it very much depends on your use case. Sometimes Cloud Run is cheaper, sometimes Cloud Functions. And actually, some App Engine also has advantages because you can actually control the instances to more extent. You pay for them, but you can actually run them longer. You can actually make sure that there are no cold starts whatsoever, but just having fixed set of instances. This is not entirely serverless, but it's an option. Now let's move to optimization of the code. And as you already learned quite a lot about serverless on this talk and in the morning, I will focus on an example, just one function and how we can optimize it. And the example that I'm going to show you is a function that converts text to images. It's something like creating memes. It's very simple. It's much simpler than you would expect. The funny thing here is that there are two parameters. One is, of course, the message that you want to put on the picture, and the other one is whether you want a background or not. You cannot select the background. You can say if you want it or you don't want it. The function takes 3 steps. Download the background from cloud storage, apply some caption, your text, and finally upload the result. 3 simple steps. And the source code is very simple. I hope it's visible on the back. So let me quickly read that for you. So first of all, we create some temporary directory where we want to store the results. We download the background file from cloud storage in the second step here. We use image magic to draw the caption, and we write the result to local disk. The result file that we use is created here is a random string, so once we upload it to cloud storage, we will not overwrite the previous results. So every time we create a new random name, that will be the result. Very simple. Let's see how it works. Let's test it at scale, and the scale will be 5 QPS for 5 minutes. And we see it works, but it breaks in about 5%. There are 5% of errors. And on the memory plot, we see that the allocation actually reaches the ceiling or slightly exceeds it at high percentiles. So this plot is, I'm sorry, in this plot, the blue line is the 50 percentile, and then there is 90 and 99, I think. So we hit the memory. Probably we haven't given enough memory to our function, so let's give it more. But before we do that, let's check if that's really the case. So we go to cloud logging, where we can see what happened. We check logs for our functions, and we see a lot of memory limit exceeded errors. So we add memory, and we test again. We double the memory, actually. And we see that the memory usage went down, but there are still errors. Sorry, the memory usage didn't go down. The memory usage actually went up, just the errors went down. So this is a pretty common pattern. You add memory, your application uses more memory. You add more memory, your application uses memory. Very simple. Probably there is a memory leak. Can you spot a memory leak here? It's actually pretty hard because there is one important piece of information that you have to know to find the memory leak. And this piece of information is that Cloud Functions, the local file system in Cloud Function is an in-memory file system. So whenever you write things to disk, let's say to /tmp, it will consume your runtime memory. So with this information, you can actually spot that the error is that we create a temporary file on /tmp, and we never delete it. And you know that instances are reused for subsequent invocations. So on every invocation, there is one more file written to the local disk, and consumes some memory. And finally, the instance crashes. Perfect. Very simple fix. Just remove the file before finishing the function. Everything works. Memory usage went down. No more errors. Everything works. Shall we reduce the memory? We could. But the speed in which your function runs is actually proportional to the amount of memory. So we give the CPU speed proportionally to the memory allocation. So in this case, the function is actually CPU intensive. There is some image processing, putting the pixels, the text into the pixels. So probably it's a better idea not to reduce the amount of memory so that your function actually runs faster, has lower latency, your users are happier. So let's try to optimize further. What is the time actually spent on? Let's go to logs. In logs, you cannot say it here, but if you go to cloud logging, there is an execution ID for every function invocation. So you can select one, right-click, and filter logs from just a single invocation. And after doing that, you cannot see here, but you can trust me that the majority of time is spent on uploading the picture, which is quite surprising. Even more surprising, downloading the background is only 80 milliseconds, and uploading the results is over a second. So that's really strange, and this was much simpler to debug. I will tell you why on the next slide, but just a quick self-correction. This is not the best way to debug performance, going to logs and checking one invocation, because you can actually draw invalid conclusions from just single invocations. Much better to report metrics. There is a service in Google Cloud called Stackdriver when you can report metrics and just have more statistical information. The problem with uploading the image, why it took so long, is that in the code I use BMP, the incompressed version of BMP. And once I switch to PNG, a compressed file format, The execution went down, the execution time went down tremendously, and it's only 0.9 seconds, so we saved a lot. The next optimization would be to optimize downloading of the background image. As you know, instances live long, so once you download something, you don't have to download it on the next invocation because it's already there. And also, some users don't really want the background. So what we'll do, we'll check if the user wants a background, and we'll check if maybe we already have it, and only if not, we will download the file. Otherwise, we'll skip it. Either we have it, well, we don't have to download it. With that change, we save another 50 milliseconds, not so much, but it adds to latency. And if you imagine that at scale, when you pay for hundreds of QPS maybe for your service, this actually is real money for you. So 50 milliseconds is significant. You can also move some computations to the global scope. If those computations don't depend on the request, they can be executed once and just cached. And in our case, this is creating the temporary directory, and this is initializing the cloud storage bucket, the global variable. With that, we managed to save another 25 milliseconds. Not bad. And from the very beginning, I think there is a huge difference. And in particular, the most importantly, the function doesn't crash. So we performed many small improvements, and you can always do similar improvements when you write code. Just keep in mind these techniques. They are all very simple, but you just have to be aware that those things actually help. And once you debug performance, you have all the platform tools, metrics logs to observe our system. And this is all, and I'm happy to answer questions, and maybe Monika can join me on stage.
Hello. I have a question. When you need some font, for example, in your system to print text in special font, what would you need to do? How you can install this font to use some library or some system or whatever to use it?
Yeah, so that very much depends on which service you want to use. In Cloud Run, it's simple because it's a container, so you can just include whatever you want in the container. In Cloud Functions, you have two options. The one that I mentioned before, that you during initialization, you actually download the font from some storage that exists somewhere. But you have to do it on every initialization. It actually maybe adds some complexity. Another option is actually to include the font together with this function source code, because you can include any binary files, and you will deploy it, and you will actually have it there. There are some limits on the deployment size, but fonts are, I think, not so large. Probably the problem is how you then use it, because usually the system expects that the font is under certain path. You will not have right permissions to that path. I don't really have a good answer to that. I think it very much depends on on the specific use case. In the case of the fonts, you probably use some libraries that use the fonts. Very often it's possible to configure things using environment variables, like start some process, and in the environment variable, you pass the font path. I think that could be the answer.
Yes, I would encourage the second option, because in Cloud Functions, we have a limit of 100 megabytes of compressed sources that you can upload, so it applies for sources, but also some additional files, like, for instance, a font. So probably the best way is just to upload, so it's always available for a function to use.
Any other questions?
I have a small question. Maybe without a microphone.
It's required.
Okay. At the beginning, you have said about auto-scaling, but are there any limits of scaling, or maybe how much will it cost for us to achieve the high scaling?
So in general, there are no limits. So if there is traffic, we can scale infinitely unless you tell us not to do so. So you can attune an infrastructure a bit. So for instance, in Cloud Functions, but also in App Engine, we can something which is called max instances. So you can limit the number of instances, like the upper bound. It's also useful when you, for instance, have functions or services that access some limited resources, let's say a connection pool for a database. You don't want to go over this limit because you will have like resource exhausted error. So we can also use this to tweak the infrastructure a little bit.
Okay, thank you very much.
And you are welcome to actually try the scale that you can reach. We do have some quotas. You can apply for more.
Is it possible to use some connection to database in this function?
Yes, like there is really no limit on what you can do. You can like access external services. Also, what could be mentioned is that if you would like to call a Google API, you have that for free in a sense that you don't have to authenticate. You can just call the API, which is like which makes like writing services very easy. But obviously, you can call anything. We also have a feature which is called VPC connector. So you can, for instance, directly go to your virtual machine without going like through the external traffic. So yes, you can connect to anything you want.
And there's actually, just one more thing, there's actually a very interesting connection between this question and the previous answer that Monika gave and your question, that the serverless functions can scale to a really large amount, and if every function establishes a new connection to the database will actually not survive. So this is why we need these max instances to limit the scale, because the cloud can scale much more than usually the database that you host, maybe not in the cloud, but in your data center.
Is it possible to use connection pool?
I think it does. In Cloud Function, it doesn't make sense, because Cloud Functions, you have always one request served at the same time, right?
No, I mean connection pool for the database.
I understand, but in case of Cloud Functions, you have one Oh, you mean connection pool that is shared between the different instances, the containers? Yes. I don't think that's possible.
Okay, so each time I need to create a new connection.
No. Each time you have an instance, you have to create a new connection, but this instance can keep the connection persistent for some time. And this instance is always single thread, single concurrent, so there is no need to have more than one connection on this instance.
Okay, so if I want to serve for about 50 simultaneously connections, I need to not I, but system needs to up 50 servers or nodes. Or
I think that's the simplest solution, because you can just have this setting, no more than 50 instances, and then you are sure that your connection pool is not exhausted. Like the other option would be that you probably write a service that manages this collection, and from a function you remotely connect to that. But that would require more coding and setting up such service.
Okay, thank you.
Thank you very much.